All right, if part one gave you the foundation, part two gives you the weapons. This right here is exactly where junior engineers fail and senior engineers completely dominate. You know why your system crashes under heavy load? It's because you might not fully grasp caching and resilience. You know why you get stuck on CAP theorem questions? Probably because you just memorized the triangle but never really understood the actual trade-offs. So today, we're hitting caching strategies, reliability patterns, messaging systems, and observability. These are battle-tested patterns from production systems serving hundreds of millions of users. If you want to sound like you've actually built distributed systems instead of just reading about them on a blog, this explainer is absolutely non-negotiable. So let's quickly lock in our roadmap for the next 10 minutes. We're moving systematically from saving your database from meltdowns to building fault-tolerant architectures, decoupling your services, and finally, completely locking down and securing your entire infrastructure. Let's get right into it. Okay, section 1. Let's dive into this first massive pillar, caching strategies and optimization. Basically, how to avoid the absolute slowest part of your system, the database. So we implement caching, right? That's just storing frequently accessed data in a super fast storage layer, like memory, to take the heat off your backend. You've really got to understand the trade-offs between the main caching strategies here. Cache aside relies on lazy loading. The app just checks the cache first. Write through updates the cache and the database at the exact same time. It's super safe, but yeah, it's a bit slower. And then there's write back, where you write only to the cache for just crazy off-the-chart speed. But watch out, because you risk data loss if that cache crashes before it syncs to the database. The thing is, memory is expensive. It's physically limited. So what happens when your cache is 100% full? Well, you need mathematical rules, cache eviction policies, to ruthlessly decide what stays and what goes. Think of your cache kind of like a pizza display case. You only keep what's selling hot right now. The undisputed king here is LRU, or least recently used, which just kicks out the oldest untouched data. Alternatively, you've got LFU, least frequently used, which boots out data with the fewest overall clicks. Now here's a fun scenario. What happens if one of your cache servers actually physically crashes? Enter consistent hashing. This is a brilliant mathematical technique used to distribute keys across nodes in a logical ring. Because you assign data this way, if one server goes down, only a tiny fraction of your cached keys actually need to move over to the adjacent node. It's beautiful math, and it literally saves you from a cascading cache miss disaster where suddenly every single request is hammering your fragile database. To optimize things even further, we deploy Bloom filters. A Bloom filter is this lightning-fast, highly space-efficient probabilistic data structure. Its whole job is to quickly answer whether an item might be in a set. I like to think of it as a super-fast bouncer at a club. It stops millions of useless database queries by blocking users from asking the database for usernames that definitely do not exist. Now, it never says definitely yes, but it is absolutely 100% accurate when it tells you definitely no. Moving on to Section 2, reliability and fault tolerance. Now, what's genuinely fascinating about distributed systems is that failures aren't an anomaly, you guys. They are the baseline expectation. Let's start with the unbreakable rules here. The CAP theorem proves that when the network inevitably breaks, which we call a partition, you have to make a hard choice. You either serve accurate data, which is consistency, or you actually stay online, which is availability. There's no escaping it. And the PACELC theorem takes it a step further. It shows that even when the network is perfectly healthy, you still have to trade off latency versus consistency. You're literally paying in speed to maintain strong consistency. And that leads us directly to your architectural choices. Are you going with strict ACID compliance? That gives you strong consistency for financial perfection, locking everything down so every user sees the exact same data instantly. Or do you go with the base architecture? This relies on eventual consistency to keep giant modern internet apps breathing. With eventual consistency, updates spread over time. And sure, nodes might briefly disagree, but the system never crashes under load. To actively defend your servers from those massive loads, you absolutely have to implement rate limiting. This controls how many requests a single user, an IP, or an API key can make within a specific time window. It acts exactly like one of those metering lights on a busy highway on-ramp. It protects your shared resources from malicious abuse like DDoS attacks or even just accidental viral traffic surges that would otherwise completely crush your API. But hey, what if the problem is an external dependency? When a third-party service dies, the circuit breaker pattern instantly trips to the open state to block traffic. Just like the circuit breaker in your house, it's an automated switch that stops your system from repeatedly calling a completely broken service. By instantly failing the request instead of waiting around for a timeout, it stops a tiny delay from dragging down your entire fleet into a catastrophic cascading failure. And we usually combine that with the bulkhead pattern. This physically isolates system resources into separate compartments, so a failure in one area doesn't sink the entire system. Think of watertight compartments on a submarine, right? If your recommendation engine thread pool completely crashes, no worries. Your payment processing thread pool is entirely isolated and keeps running flawlessly. Now, for temporary network blips, retry patterns are essential. But listen, if you just retry blindly, you're going to accidentally DDoS your own struggling servers. You have to strictly use exponential backoff. That means each retry waits exponentially longer than the previous one. Say 1 second, then 2 seconds, then 4 seconds. Spacing it out like this gives the target service the actual breathing room it desperately needs to recover. Here's the catch, though. Retries are incredibly dangerous unless your API guarantees idempotency. That's a fancy word for a mathematical guarantee that doing an action multiple times yields the exact same result as doing it just once. So, if a user angrily hits pay twice because of a network timeout, the server recognizes the unique idempotency key, ignores the duplicate, and just hands back the original success message without double charging their credit card. To orchestrate all these nodes and handle failures smoothly, load balancers rely on rapid heartbeat signals. A heartbeat is exactly what it sounds like, a periodic ping sent between servers broadcasting, "Hey, I'm still alive and working." If a central coordinator misses, say, 3 consecutive heartbeats, it continuously detects that and routes traffic away from the dead server in real time. And to prevent nasty data corruption during these network splits, something we often call a split brain disaster, distributed clusters use leader election algorithms. This is a process where multiple servers securely vote to designate a single leader to coordinate tasks. By using consensus algorithms like Paxos and Raft, we make sure that all nodes agree on one single, undisputed source of truth. All right, section 3. Let's look at how we build on all of this to completely decouple our architecture so massive traffic spikes get absorbed gracefully. Enter message queues. Think of a message queue as a digital waiting room for tasks that entirely separates the producer from the consumer. Using point-to-point queues or pub subsystems, heavy background jobs like processing payments or sending out thousands of emails won't block the user's immediate request. It just absorbs massive bursts of traffic. And if a task repeatedly fails, no big deal. It's safely pushed over to a dead letter queue for you to investigate later. For complex e-commerce flows, we absolutely want to avoid locking databases. Instead, we handle distributed transactions using the Saga pattern. The Saga pattern takes a massive, sprawling distributed transaction and breaks it down into local, step-by-step actions. If any single step fails along the way, it triggers a chain of compensating actions. Basically, it's an automated undo button specifically written to reverse the previous changes. This localized, step-by-step approach is exactly why Saga replaced the older two-phase commit, or 2PC protocol. Now, 2PC gives you perfect instant consistency by making a coordinator ask all databases if they can commit, kind of like a wedding vow. But it creates a highly dangerous single point of failure. Because if the coordinator crashes during phase 1, all your servers are stuck holding locks, and that will completely bring modern internet scale throughput to a grinding halt. Okay, final section. The ultimate sign of a senior engineer is knowing that a system is never really finished until it is securely locked down and fully observable in production. First up, you've got to leverage distributed tracing. This lets you track a single user's request as it jumps across dozens of different microservices. To track performance, think of SLIs, service level indicators, as your raw speedometer readings. You use those exact metrics to ensure you're meeting your SLOs, which is your internal speed limit goal. And you do all of this to guarantee you never, ever breach your SLAs. That's the legally binding ticket you have to pay the client if your system crashes. On the security side, you need to delegate authorization without actually sharing passwords, which is exactly what OAuth 2.0 and OIDC are built to achieve. You've also got to secure the transport layer via the TLS handshake, guaranteeing encryption in transit. And fundamentally, you have to enforce a strict zero-trust architecture. That means every single request, whether it's internal or external, is aggressively verified as if it originated from a highly hostile network. And there it is. You've just completed the full system design foundation. Part 1 gave you architecture, networking, and databases. Part 2, we just crushed caching, reliability, messaging, observability, and security. Honestly, this isn't just for interviews. This is exactly how the giants like Netflix, Amazon, and Google build production systems serving hundreds of millions of users. You now have the exact architectural blueprints. But keep in mind the golden rule of distributed systems. There are no perfect architectures, only perfect trade-offs. The real question is, when you sit down to build your next massive system, which trade-off are you willing to make? Thanks for watching this explainer. Like, subscribe, and let me know in the comments which system you want designed next.